Let's find all asymptotes, intercepts, and holes and use them to help graph the rational function. Up first, we want to find domain. Recall that in order to find domain, we set the denominator equal to 0. To help us, let's go ahead and factor that denominator. We want two numbers that multiply to -12 and also add to +1. That will be 4 and -3. Again, we set the denominator equal to 0, so we're going to set each factor then equal to 0. And we'll solve each of these. X equals -4, x equals 3. And we're actually going to say not equal to because those are domain restrictions. And recall there's two different ways to denote the domain. One is set notation, all x such that x is not -4 and x is not 3. An alternate way to denote the domain is using interval notation. We have -infinity up to -4, union -4 to 3, union 3 to infinity. To find vertical asymptotes, we want to reduce the rational function if possible, and then set the denominator equal to 0. To help us see if we can reduce, we need to factor the numerator. So let's do that off to the side. Since we need the AC method, we've got to do a little bit more work. AC is 6. Two numbers that multiply to 6 and add to -7 are -6 and -1. So we have 2x squared minus 6x minus x plus 3. Looking at the first two terms, they have a 2x in common. Factor out the 2x and we're left with x minus 3. The last two terms have a -1 in common. Factor it out and you're left with x minus 3. Finally, we factor out the x minus 3 and we're left with 2x minus 1. So we'll put that in the numerator. X minus 3 times 2x minus 1. Notice that x minus 3 occurs in the numerator and denominator, so that's going to reduce, leaving us with 2x minus 1 over x plus 4. Again, to find the vertical asymptotes, we look at the reduced denominator and set it equal to 0. So x plus 4 we're going to set equal to 0 and solve. We get x equals -4. That's the equation for the vertical asymptote. Notice that there are two domain restrictions. We had -4 and 3 that are issues. Only -4 is caused by a vertical asymptote. That means the other domain restriction must be a hole in the graph. And we know that because it's the factor that reduced, that factor that cancels, that's going to be a hole in the graph. So we're going to use that factor to find the hole. X minus 3, set it equal to 0, and we see that the hole occurs when x is 3. To find the y value, we're going to plug 3 into the reduced rational function. So 2 times 3 minus 1 over 3 plus 4. We get 6 minus 1, which is 5, and 3 plus 4, which is 7. So the hole is at 3, 5/7. To find horizontal asymptotes, we compare the degree of the numerator and denominator. Recognize that the degrees are the same. Both of these are a second degree polynomial. Since the degrees are the same, we're going to look at a ratio of the leading coefficients. The first numerator has a 2, and the first coefficient in the denominator, you don't see it, but there is a 1 there. So we're really looking at 2 over 1, or simply 2. That means the horizontal asymptote is y equals 2. We don't have an oblique. Since we have a horizontal, there is no oblique asymptote. To find x-intercepts, like always, we set y equal to 0. But since this is a rational function, we can actually take a shortcut. Instead of setting y equal to 0, we can look at the reduced fraction and set the numerator of the reduced fraction equal to 0. So 2x minus 1, set it equal to 0. We get 2x equals 1, or x equals 1/2. So the x-intercept is 1/2, 0. To find the y-intercept, we set x equal to 0, like we've always done. And it's probably going to be easier to use the original version rather than the factored version. Notice that when you set x equal to 0, this term goes away. Set x equal to 0, this term goes away, and you're left with a 3 in the numerator. In the denominator, set x equal to 0, that goes away. Set x equal to 0, this term goes away. You're left with negative 12. So this reduces to negative 1/4, meaning the y-intercept is 0, negative 1/4. Now we're going to throw all of this together on a graph to get a sketch of the graph. So I'll draw a dotted line to represent x equals negative 4. Bear with me with all the scrolling. The horizontal asymptote is y equals 2. And now we can look at the intercepts. The x-intercept is 1/2. The y-intercept is negative 1/4. We also know that there is a hole in the graph. The hole is at 3/5/7. 3/5/7 is roughly 0.7. So we're just going to approximate where that is. And using these points, we can assume what this side of the curve is going to look like. We've got these asymptotes, and it's going through those points. And we've got a rough sketch of part of the graph. Notice that we don't have this part of the graph over here. We know there has to be something over here due to the domain that we found earlier. So if we wanted to algebraically find these and get a sketch, we would just plug in some values, like -5, plug it into the function, see what we get. -6, plug it into the function and see what we get. And continue doing point plotting to get some additional points. To save some time, it might feel like a little bit of a cheat, but we're going to graph this to see what the rest looks like and confirm what we have is correct. I like to use alpha y equals to get the pretty fraction that makes this a little bit easier. So we have 2x squared minus 7x plus 3 divided by x squared plus x minus 12. It's always a good idea to double check, make sure you don't have any typos. And then we'll go to the graph. And it looks like we're pretty good. It looks like the curve is up here in the second quadrant. We can use the trace feature to get a point that's close by. So let's just approximate that. That's roughly -6.6. Again, very, very rough estimate. -6.6. Right in there. We can use that to kind of help us get a little bit of a curve. Again, we're going for a very rough sketch here. We're not going for crazy accuracy. The main thing that we're going to be focusing on is algebraically finding those points from earlier, like the domain, intercepts, asymptotes, holes, all of that stuff.